Okay, so let's say, for example, that on Sunday, I go to the bank and I deposit $50. And then on Monday, I go to the bank and I deposit $50. And then on Tuesday, I go to the bank and I deposit $50. And then on Wednesday, I go to the bank and I deposit $50. So Sunday, Monday, Tuesday, Wednesday, I went to the bank and I deposited $50. Would you expect me to also go and deposit $50 on Thursday? Yeah, it seems likely that I'm gonna go deposit $50 on Thursday. So do I necessarily have to deposit $50 though?
No.
No, exactly. So the expectation there is that, oh my gosh, look, she went to the bank every single day this week so far and she deposited $50. It seems really likely that she's going to deposit $50 the next day on Thursday as well. But let's say that I want to deposit $50, but instead I get the flu and I can't go to the bank, and so I don't. How much money did I deposit?
200.
No, how much money did I deposit on Thursday?
Oh, my bad.
0.
0. Okay, so here the expectation is that I would deposit $50. The reality is that I deposited $0, right? So that expectation, when thought of in terms of math, is like the limit. So here we can say on Monday, I deposited $50. On Tuesday, I think I actually started with Sunday. On Sunday, I did it. On Wednesday. But then on Thursday, I'm sick, I don't go to the bank, and I therefore deposit $0. So here we can say that my expectation is that on Thursday, I will deposit $50 as well. My reality here is that on Thursday, I deposited $0. So my expectation is like what's called a limit in math. So here we could actually say that the limit as days approach Thursday is $0. So as the days get closer and closer, is $50. As the days get closer and closer to Thursday, we see a pattern developing. That pattern gives us this expectation that 0 is going to happen. So what would happen if we were to now think of this as something a little bit more mathy? So we have this idea of expectation versus reality. Let's think about this in terms of a function. So let's say that I have the function So I have this function, f of x is equal to x squared plus 1. Now, here we're going to do something a little bit different. We're going to look at like a chart of numbers. So if I were, for example, to say, let's say have x squared plus 1 here, what happens when I plug 1.9 into x squared plus 1? So in other words, what is f of 1.9? You guys have your calculators, you can plug in, tell me what you get.
4.61.
4.61. So here, the actual value is 4.61. What happens when I plug 1.99 in?
4.9.
4.9601.
Perfect, 4.9601. 4.9601. What happens when I plug 1.999 in?
4.996001.
Perfect, 4.996001. Okay, so this is a little bit different than the money example, but what are those numbers up top approaching? 1.9, 1.99, 1.999. So like, if we saw Sunday, Monday, Tuesday, Wednesday, we know that clearly the next day is Thursday. Those days are getting closer to Thursday. 1.9, 1.99, 1.999. What are those numbers getting closer to?
2 and the other one is 5.
2 and the other one is 5, exactly. So this here we have 4.996001. So I'm not going to plug in 2. But what would I expect to happen if I did plug in 2?
5.
5. I would expect 5 to happen because those numbers are getting closer and closer and closer to 5. So what we can see is that these numbers are getting closer to 5. Well, these up here are getting closer to 2. So the expectation is that when those numbers get to 2, the value of x squared plus 1 will be 5. And if we think of this in terms of this new idea, this limit, this is saying that the limit as that x value approaches 2, so this is our x value, is 5. Because that is the expectation, that is what we think will happen. How do we write this in terms of math? We write this with an LIM, and then below that LIM, so that LIM is limit, we say that as x is approaching 2, so we have the limit as x approaches 2 of what? Of x squared plus 1, so that x squared plus 1 goes out to the side, and then we say that it equals to 5. So we can read this, the limit as x approaches 2 is 5, or we can say the limit as x approaches 2 of x squared plus 1 is 5. are there any questions about this so far? About this idea of a limit so far?
No.
No questions? Okay. So what about the reality? Back here, we talked about when we were looking at Sunday, Monday, Tuesday, Wednesday, Thursday, our expectation was that $50 was going to happen, but it turned out that $50 didn't happen, $0 happened. So our reality was 0. Well, how do we represent the reality in math? This is something that you guys have already done a lot. So what is the reality? The reality in this case would be what happens when we actually do go and plug in 2. And what happens when we plug in 2?
Gives 5.
It's just 5, you got it. So notice the reality, the notation that I use for my reality is just plugging that value into my function, f of 2. That's my reality. In this case, are my reality and my limit the same thing?
No.
Was my reality 5?
No.
Huh? Was my reality 5?
Oh,
No.
yeah.
It was-
Yeah.
Yes. F of 2 equaled 5. You guys see that? My reality was 5. So we had f of 2. I plugged in 2 to my function. I got 5. Was my limit also 5?
Mhm.
Yes. So in this case, my reality and my expectation were the same thing. In the money case, were my reality and my expectation the same thing?
No.
No. So the reality and the expectation don't necessarily have to be the same, but as we see in this example, sometimes they can be.
Okay.
So what we're going to do with limits, we're actually going to learn them in 2 different ways. We're going to start off by looking at graphs, and we're going to try to understand expectations and reality from graphs. And then after that, we're going to learn how to calculate limits with actual functions. So really, we're going to be doing limits twice. Are there any questions about what a limit is telling us before we go on and look at the main graphs?
Can you, can you show an example, like a mathematical example, where the reality would be 0, but the limit would be 5? Because like,
Yes. Where the reality would be 0. So the answer is yes, but there are things that we have to do for you to be able to understand it before.
okay.
So like it's hard for me to show you one of those right now because it involves
Okay.
like a lot of factoring in techniques for calculating limits that we just haven't learned yet.
Okay.
But we're going to see that happen in a graph. And so first you'll see what that looks like before we go and see an actual function.
All right.
I can make it happen right now even. So you said reality 0, limit 5?
Any numbers, just as long
Okay,
as they're
all right.
different.
Okay, so we're going to start off just by looking at a graph now. So we're going to call this function f of x. Okay, so I've drawn the graph. I'll give you guys a second to get the graph drawn as well. Notice I put little holes, like little holes, so make sure that you include those in your graph. They're important. So just in the chat, give me like a little smiley face or just a yes or something to let me know that you're done getting the graph down.
The point is 2, 3. Well,
The-
the expected point. Like,
Yeah, 2, 3, 2, 3, you got it.
Okay, 2, 3. Okay, good.
Thanks, Maureen.
If it's like an absolute function, absolute value function, right?
All right, that's a lot of you. Okay, so let's start off by looking at the limit as x approaches 1 of f of x. So what this is asking me to do, so I'm just going to go back up for just a second. Notice here, when I was trying to develop an expectation for what happened to x squared plus 1, did I look at 2 or did I look at values close to 2?
Value is close to 2.
I looked at values close to 2. So I want to know what the expectation is at 2, not what the actual value is, not what the reality is. So when we're doing limits, we're looking at expectations. So what this is telling me to do, this is saying, look at values that are not 1, but that are close to 1, and develop an expectation about what you think would happen at 1. Okay, so with that said, I'm going to look at values that are close to 1, but not 1. So that's like looking at values maybe on the left side of 1, maybe on the right side of 1. So to figure this out, and hopefully some of you have seen it already, I'm going to go up to the graph, but I'm looking at values that are left of 1 and values that are right of 1. So values that are really close to 1. And as I follow the graph along and get closer and closer to 1, I want to be looking at what is happening to my y values. So as the x values get close to 1, what happens to the y values?
Wait, what's the question?
Yes. So as the x values get close to 1, what happens to the y values? You guys have an answer for me?
Goes up.
To what value? What value are the y values getting closer to?
1.
1.
You got it. So the answer here is that this is equal to 1 because those y values are getting closer and closer to 1. Uh-oh. Hang on. Oh, there we go. Okay. Do you guys still hear me?
Yeah.
Yeah.
Okay, good. So what happens to the y values as the x values get closer and closer to 1? Those y values get closer to 1. So this right here is my expectation. My expectation is that those y values are getting closer to 1. Now, f of 1, this is my reality. So this says, what's happening at 1 exactly? So this says, go to 1, to 1 itself, go up to the graph, and what value am I at when I go up to the graph there?
1.
Also 1. So in this case, are my expectation and my reality the same?
Yeah.
Yes. So this is my reality. And in this case, just we can note that expectation equals to reality. Now, what if I were to do the same thing, but for 2? Again, this says go to 2. Don't go to 2 exactly, but instead go to values that are to the left and right of 2. And go up to the graph and let your values, your x values, get closer to 2. And what's happening to your y values as you do that?
Get closer to 3.
They get closer to 3, exactly. So we can see that we would expect to end up at 3. By looking at what's happening around 2, we would expect our y values to end up at 3. So this is my expectation. What's my reality here?
It's not 3.
It's not 3. Where do I end up instead?
0.
0. So in this case, f of 2 is equal to 0, and my expectation does not equal to my reality. So we can see that that's equal 0 because we have that dot that's like posted right there. So that dot is saying this is the reality. Are there questions about that?
Yeah, why is there a dot? I'm confused.
That dot is saying that that is the value that this function takes at that point. So that hole in the graph is saying, nope, if I plug in 2, I'm not going to get 3. That function does not take the value 3. It takes the value that happens at that closed dot.
Okay.
So like, for example, when I've drawn this graph, I didn't draw all of the points as dots, but if I were to ask you for f of 3, for example, so like we said f of 1 was equal to 1. There's not a closed dot there, but drawing that closed dot helps us to more easily see that. What's f of 3? What is f of 3?
Is it 5?
It's 5, yeah. So like, it's kind of like there's a closed dot there. That dot tells you that this is the value the function takes. If we think of this in terms of depositing money, and let's say that 1 is Monday, well, on Monday we deposited $1. On Tuesday, we expected to deposit $3, but we actually deposited $0. If 3 is then Wednesday, on Wednesday we deposited $5. Does that kind of help? Okay, so then what about -3? The limit as x approaches -3 of f of x, what do you guys think that equals?
0?
So -3,
It does not
Oh, no,
exist.
the limit. Oh,
the limit, yeah.
-2.
So I'm at my -3. I want to look at the left side of -3 and the right side of -3. I go up to the graph and I'm going to like walk along my little graph. So I'm walking along my little graph. What value do I get closer to?
2.
2. So what do I expect to happen?
2.
I expect 2 to happen. So this is my expectation. Is there a closed dot anywhere?
No.
No.
So what's the reality?
Does not exist.
Does not
Yeah.
exist, exactly. So in this case, the lack of closed dot tells me that -3 is not in the domain of this function. It just doesn't exist. So f of -3 does not exist. And here we can write, this is because there is no closed dot anywhere. And so my expectation does not equal to my reality. My reality is that -3 is not in the domain of f of x. Okay, so this can be a little bit confusing for some people the first time that we look at it, this idea of separating a graph into limits and functions, expectations and realities. So we're gonna look at another graph really quickly, and hopefully that will help to kind of help you absorb this. Do you guys need a few seconds here, or can I go up?
I'm good.
Okay. So I'm going to call this function h of x. Oops. Okay, so again, tell me in the chat when you guys have the graph done. And then we're going to think about the answer to this question. For which x values would the expectation not meet the reality? Good. So take a second to think about the answer to the question. It seems like most of you guys are ready. For which x values would our expectation here, so our limit, not meet the reality? Tell me in the chat or with your voices. It's okay if you're wrong.
H of -2 and h of 3.
You got it, exactly. It's going to be -2 and 3. So those are going to be the places where we care the most about limits, because those are the places where things aren't what we would expect them to be. So I'm going to look at the limit as x approaches -2 of h of x, and I'm going to look at f of -2. Okay. So again, how do we determine our expectation? For our expectation, we don't look at -2 itself, we look around -2. So I go to the left side of -2 and I go to the right side of -2. It can't be that dot because there is no graph around the closed dot. I need to go up to where there is graph. Around the closed dot, there is no graph, so that's definitely not my limit. I'm using the graph to make these expectations. So I go up, and when I'm on the left side or on the right side, what y value do these things seem to be getting close to?
-2.
Positive 2.
Oh, +2. Yeah.
Yeah.
Okay.
So exactly. So this is going to be a positive 2. We see the y value. So as x gets closer and closer to -2, y gets closer and closer to 2. So that's my expectation. What's my reality here?
0 or nothing?
Where is my closed dot?
1.
Oh, 1.
1, exactly. So my reality is that closed dot. We're saying we expected for 2 to happen, but it turns out 1 happened instead. So this is equal to 1. And that is where we have the closed dot. So here, my expectation does not equal to my reality. Are there any questions about this yet? You guys mostly getting it? Feeling confused?
I don't understand how you got 2.
How I got the 2?
Yeah.
So if I were to actually go and what I'm looking at, I want to know what happens as my x values are not -2, but as they get closer and closer to -2. So like the values that I would be looking at here, what's a value that's to the left of -2, but really, really close to 2?
Like -2.1.
-2.1, exactly. So like, let's say that I'm at like -2.1. What other values could be to the left of 2, but close to 2?
-2.05.
Why don't we go with -2.01?
Okay.
And then
Yeah.
-2.001. So if I look at these values that I just wrote, are those values getting closer to -2?
Yeah.
Okay, so these are my x values, right? So if I were to go and look at the graph here, so I have my graph of h of x, what is the value that this graph takes at -2.1? Notice it's just a straight line right here. So if
2.
I'm at -2.1, where is it?
2.
2, right? What about -2.01?
2.
2. What about -2.001?
2.
2. So as I'm getting closer and closer to -2, as these values are on their way to -2, what would I expect these values to be getting close? What seems to be happening?
They're all 2.
They're all 2. So let's think of this again in terms of money. On the first day, I deposited $2. On the second day, I deposited $2. On the third day, I deposited $2. How much would you expect for me to deposit on the fourth day?
$2.
$2, right? So what we're seeing as when we're at the left of -2, those values, they're 2 and they're just staying 2. It's a little bit harder to do this chart on the right side because we don't actually have the values, but what y values? So if I go over here, I'm like at this y value, and then those y values are getting bigger and bigger and bigger. What do they seem to be getting closer to?
2.
to 2. Like if I'm on the right side over here, hang on, let me redraw it. I just erased it by accident. If I'm on the right side over here, and I'm like, okay, so here I have this y value, and then I'm gonna look at this y value, and then I'm gonna look at this y value, and then I'm gonna look at this y value. As those values, as my x values are getting closer and closer to -2, what's happening to those y values?
They're increasing.
And what are they increasing towards?
2.
2. So that's why my expectation is 2. However, when we get to 2, we have that open dot. And that open dot tells me, but guess what? 2 didn't happen. What happened instead?
1.
1. We have the closed dot at 1. 1 happened instead. Did that help?
Closed dot at 1.
Yes, Alex. So here I'm going to do it in another color. There's this closed dot right here. What's the y value that goes with that closed dot?
2.
If I go over, what's my y value?
What do you mean by if you go over?
Like if I look at the y-axis where I have the y values written,
Okay.
what y value is that?
It's 2.
2 is up here, right? Is that dot at the 2 level? Is the closed dot?
Oh,
at
the closed one. Oh my
yeah, the
bad.
closed one.
That 1.
It's at the 1 level, right? So that closed dot is telling me that 1 happened. Whereas this
Oh.
open
okay.
dot is at the 2 level. It didn't happen, but that open dot is the thing that the graph was getting closer to.
Okay.
Does that kind of make more sense?
Yeah.
Okay, so with that said, let's do the other value that we said. We said up here, we expect for the x values to not meet the reality at -2 and 3. So what then is the limit as x approaches 3 of h of x? What's my expectation? What does it look like it's
2.
going to happen?
2.
2.
2. But what actually happens?
Nothing.
Nothing. Hang on. Nothing happens. So f of 3, I'm sorry, not f, h of 3. My bad, up here as well. H of 3 does not exist because there is no closed dot. So my expectation does not meet my reality. Are you guys starting to get the hang of this?
Yeah.
Yep.
Because we're going to add something now. So we know that limits are our expectation, which does not necessarily have to be our reality. Actually, let's just do one more here. If I were to do the limit as x approaches 0 of h of x versus h of 0. What's h of 0?
0.
It's just 0, right? I don't have to have a big dot there because my graph doesn't have like a hole in it. It doesn't stop. It's just saying, hey, look, it does go nicely through that point. What would I expect to happen if I looked at the left side of 0 and the right side of 0?
0.
I would also expect 0 to happen. So in this case, is my expectation equal to my reality?
Yes.
Yes. Notice, why did I write not equal? Notice that in this case, the graph is just nice and pretty. There's no like open dot or anything like that. Okay. Questions before we add something? Okay. So what's a vertical asymptote?
Isn't that when like a point along the x-axis in which the graph comes close to but it never reaches?
Exactly. Good. So it's like saying you have something that the y value is getting closer and closer to it, It's getting closer to that x value, but it never actually touches it. So it's getting closer and closer and closer. What's a horizontal asymptote?
Same thing, but for the x, like on the x-axis.
Yeah, no, exactly that. So the thing is, horizontal asymptotes and vertical asymptotes can be easily talked about by using limits. So we're going to see what happens in the graph with our expectations if we have vertical and horizontal asymptotes. Yeah. All right, I'll give you guys a second. Let me know in the chat when you've got the graph down. I'm gonna run get water while you guys are doing that. So, all right, a lot of you are finishing up. I'll give you guys a couple more seconds. Okay, so which y value here, I mean not y value, which x value here looks similar to the things that we were doing in the previous problem? Where is a place on this graph where it seems like our expectation will not meet our reality?
-1.
-1. So we'll start off by looking at that. So if I have the limit, actually let's call this graph g of x. So the limit, as my x values get closer to -1 of g of x. So what do we expect to happen here?
2.
2, you got it, exactly. I go over to -1 and I'm like, okay, I'm gonna look at the right side of -1 and the left side of -1. Hey, look, if I follow the graph and I let my x values get closer and closer to that -1, my y values are getting closer and closer to 2. What's my reality here?
3.
3. So a thing that you might be noticing is that closed dots are often the reality. Open dots are often the limit. And it's kind of helpful to think of things in that way as well. Okay, so the next thing I want us to look at is the limit as x approaches 2. So in the same way, what this is telling me to do, it's saying go to 2, so that's 2. Let's look at the left side of 2 and the right side of 2 and see what's happening as those values get closer and closer to 2. So I'm going to go out to my graph and I'm going to follow my graph. What's happening to my y values as those x values get closer and closer to 2?
Exponentially increasing.
So what are they getting closer to?
Infinity.
The 2.
They're just going to keep getting bigger and bigger and bigger forever. They're never going to stop getting bigger. Well, what is bigger and bigger forever? That's infinite. Is the same thing happening on the right side?
No, it's going down. Wait.
Huh? So I'm not going away from 2. I'm still going up towards 2. So I'm taking my graph. I'm on the graph now, and I'm following that graph, letting my x values get closer and closer to 2. Are those y values still going up forever?
Yep.
So here, we typically don't write equals because does infinity exist? Infinity is an idea of bigness. It doesn't actually exist. It's the idea of getting bigger and bigger forever. So here we usually write a little arrow instead of an equal sign, 2. So what this is saying is that as my x values get closer and closer to 2, the y values are getting bigger and bigger forever. And I don't know why I wrote 2. I meant to write infinity. Amazing, Audrey. As the x values get closer and closer to 2, the y values are getting bigger and bigger forever. This means infinity. Are there any questions about how we got that infinity?
No.
That infinity means vertical asymptote. So this tells me then that there is a vertical asymptote at 2. If the limit is infinite, then there is a vertical asymptote. So if the limit as x approaches some value, I'm going to call a, of f of x is going to infinity, but it turns out it could also be negative infinity. So I'm going to write plus or minus infinity here. Then f of x has a vertical asymptote at x equals a. Are there any questions about this? So when you're done, take a second, tell me, does this function, g of x, have a horizontal asymptote? Based on your memory of horizontal asymptotes, does g of x have one?
Yes.
Where?
On
One.
y is equal 1.
Y is equal to 1. Okay, so let's look at that horizontal asymptote. My horizontal asymptote is right here. Why is it a horizontal asymptote? It's because, yeah, David?
Well, it's because of the function and there's a dotted line, which indicates that it'll never reach the point.
Yeah, so there's that dotted line there that tells us that these y values are getting closer and closer to 1 without ever actually touching it. So, question, what's happening to my x values as those y values get closer to 1?
They're increasing in infinity, or
Exactly,
no end.
exactly that. They're getting bigger and bigger and bigger forever. So here we also have a horizontal asymptote. I'm having some spelling issues today. Horizontal asymptote. And that horizontal asymptote is what's happening because on the right, the y values are getting closer and closer to 1. As the x values get big forever.
I have a question.
Yeah.
Back to like this applies to both. So we're doing the limit. We're checking to see the limit is supposedly infinity. Is the reality also infinity, or?
There is no reality in this case.
Okay.
Yeah, so in this case, we would say, so like if I were to go up here, and I guess we can write this, it's probably important. In this case, g of 2, is there a closed dot anywhere?
No.
Is that function ever going to go anywhere, or is it just going to
No.
keep getting bigger forever?
Mm-hmm.
So in this case, we say that g of 2 does not exist. So 2 is not in the domain of g of x. And in a second, we're going to see that that's not actually always the case. It's just the case in this particular graph that I drew. Okay, I'm going to go back down a little bit. So what symbol do we use for getting bigger forever?
Infinity.
Infinity. X values get big forever, so that's infinity. So for horizontal asymptotes, what we're doing is I'm looking at the limit as x. What's happening to x? It's getting bigger and bigger forever. It's going to infinity of my function, which was g naught f. Okay, so this is saying as x gets bigger and bigger forever, what's happening to y?
It gets closer to 1.
It gets closer to 1, exactly. So if we look at the graph here, if I let x get bigger and bigger forever, so I'm going off towards the right, I'm following the graph off towards the right, I'm following this red line that I've drawn right here. So this is x getting bigger and bigger and forever on its way to infinity. My y values are getting closer and closer to 1. So here, this limit right here is equal to 1. Are there any questions about that? So this tells me then that g of x has a horizontal asymptote at y equals 1? What if I were to look at the other side of the graph? So instead of saying infinity, I'm going to let x get bigger and bigger negatively forever. So I'm looking at the limit as x approaches negative infinity of g of x. Let's go back to the graph. This is saying now go to the left side of the graph. Start and follow the graph, walk along the graph. What's happening to my y values now?
So repeat that.
Okay, so I went to the left. So this is saying what happens as I let x get bigger and bigger negatively. So x is on its way to negative infinity. So I'm saying what's going on with my y values here? Well, if I go to the graph and I follow the graph, what's happening to my y values?
Negative
Smaller
infinity
and
to
smaller and smaller.
Forever. And
Yeah.
smaller and smaller forever, what would that mean?
negative infinity.
You got it. Exactly that. So here, this would be, and I'm going to draw an arrow because remember we said infinity doesn't exist. It's just an idea of bigness, is approaching negative infinity. And here this tells me that g of x does not have a horizontal asymptote on the left side. Because I didn't get a number, I got infinity.
But can't you also say that it doesn't have a vertical one either?
We can, except that this limit's not going to give me that information. So
Oh, okay.
this is important because what we've just seen is vertical asymptotes happen when we get infinity. Horizontal asymptotes happen when we evaluate limits at infinity. But this right here, this last case, we do not consider this a vertical asymptote because both are infinite. If you guys look at this graph, does that look like a vertical asymptote to you?
No.
Hopefully you guys know what vertical asymptotes look like by now. So all this tells us, it doesn't tell me there's a vertical asymptote at x goes to negative infinity. It just tells me there is no horizontal asymptote. So the next thing is we can say that if the limit as x approaches infinity of f of x is equal to c, or the limit as x approaches negative infinity of f of x is equal to c, then f of x has a horizontal asymptote at y equals c. If, however, one of those limits is infinite, the only information that gives me is that there is no horizontal asymptote. So here we can say C does not equal positive or negative infinity. So this is kind of expecting a lot from you in terms of remembering horizontal and vertical asymptotes from high school. So if you are a little bit confused, you should really let me know. Okay, you guys good?
Yeah.
Okay, so we're gonna look at another graph and we're just gonna kind of put all this stuff together and then we're gonna add another thing. Okay, let me know when you have the graphs down and you are ready to evaluate some expectations. Actually, I forgot that part, sorry. I just added the little thing, guys. All right, we got about 5 people already. Don't forget to come let me know. Okay, so let's start off with the first type of thing. Let's look at the limit as x approaches 2. We're going to call this f of x, and let's look at f of 2. So what do you guys think? What's the limit as x approaches 2?
3.
You got it. Exactly. Not only is that where the open dot is, but if we go to the graph and we look at the left side and we look at the right side, it's going to the same place. So the answer here is 3. What's the reality? What's actually
1.
happening?
1.
1, you got it. So f of 2 is equal to 1. My expectation is not equal to my reality. Okay, next. So what if I were to look at the limit as x approaches -1 of f of x? What's going on here?
It's going to minus infinity. Well, it's expected to go to minus infinity.
Is expected to. So this is our expectation. Our expectation is that it's just going to keep getting smaller and smaller and smaller forever. So because when I look at the left side of -1 and I follow it down, my y values are just getting smaller and smaller. If I go to the right side and I follow my graph, so I'm going out on the left side and then going back towards -1. Out on the right side and back towards -1. So I should always be moving towards -1. Those values are getting bigger. What about f of -1?
It's equal to 3.
It's equal to 3. Did this graph just intersect its vertical asymptote?
Yeah.
Yes, it did. Keep that in mind. We're going to talk about it after we finish these limits. So again, these do not equal. So here we got that this was equal to infinity. Our limit was infinite. It was -infinity. So this tells me that f of x has a vertical asymptote at x is equal to -1. We got infinity, therefore we have a vertical asymptote. Okay. Next, we're going to look at the limit as x approaches infinity of this function. Well, what this is telling me is to go to the very right side. So we're saying x goes to infinity, let x get really, really big. What's happening to my y values?
Approaching 1.
You got it. Exactly. So there my y values are getting close to 1. So this tells me that I have a horizontal asymptote at y equals 1 on the right side. Okay, what if I were to look at the limit as x approaches -infinity of my function?
It'd be 2.
It would be 2. You got it. That would be 2 because that's saying now go to the left side of your graph. I'm over here on the left side and let x get really small. What's happening to my y values? They're getting closer and closer to 2. So this tells me that I have a horizontal asymptote over here at y equals 2 on the left side. How many horizontal asymptotes can a graph have?
2.
2. I can have one over on the right side and one over on the left side. There's infinity and there's -infinity. Are there any other infinities that we could evaluate? So a graph or a function can have a maximum of 2 horizontal asymptotes. However, it doesn't have to have 2. It can be like in the case of the last graph we saw, it only has 1. Or it could have none. So a function can have a maximum of 2 horizontal asymptotes. Can a function intersect its horizontal asymptote?
I'm kind of lost with something.
Okay, yeah, what's up, Ellie?
Yeah. So on the right side, what did you write after that? As x2?
As x goes to infinity.
Oh, I thought that was a 2. Okay. Sorry.
Sorry. Yeah, if you can't read my handwriting, sometimes please tell me. It is not always beautiful. Mostly it looks like this. Okay, so I ask again, can a function intersect its horizontal asymptote? In other words,
Yeah.
can it touch it?
No.
No.
Well, we just did that, no?
So look at this. Let's go and look at 1, y equals 1. So what I'm asking is, are there other places where I could have y equals 1? Could this touch y
Oh,
equals 1?
Yeah.
Yes. For example, does this graph touch y equals 1 numerous times?
Yeah.
Look, is there a point right here, and 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 right here?
Yeah.
Oh, and hey, look, right there as well, and then right here.
Mm-hmm.
How many times does this graph intersect y equals 1?
8 times.
1, 2, 3,
7,
4,
7.
5, 6, 7, 8 times.
Oh, wait.
So the answer is yes, a function can intersect its horizontal asymptote. How many times?
Unlimited, like as many as you need, like. you can.
Unlimited, as many times as it wants. So a function can intersect.
Isn't that the definition of a function? It's like the x can never intersect, but the y's can.
Exactly, and we're gonna get to that when we look at vertical asymptotes. Exactly, so like I can have the y values over and over and over again, right? Those can happen numerous times, but, well, we'll look in just a second. A function can intersect its horizontal asymptote an unlimited number of times. Okay, are there any questions about that idea?
No.
Good. How many vertical asymptotes can a function have?
Unlimited.
1.
Unlimited. It can have an unlimited number of vertical asymptotes. So like I have that dotted line there, I could have another one at 1, I could have one at 2, I could have one at 3, I could have one at every single value. Maybe I could have something like this happening. And I just have those vertical asymptotes over and over and over again. You guys kind of see that? I know that's a really incredibly rough, ugly graph, but do you guys see what I'm talking about?
Yeah.
Okay, those of you that do not have your videos on, you can tell me in the chat, please. Or turn on your microphones, give me feedback. So, how many vertical asymptotes can a function have?
2.
That's horizontal.
No.
How many vertical?
Infinity.
Infinity.
Fuck.
Look here, I just drew one that has 1, 2, 3, 4 vertical asymptotes. A function can have an unlimited number of vertical asymptotes. However, David, I think we're going to get to your confusion in just a second. A function can have an unlimited number of vertical asymptotes. However, how many times can a function intersect its vertical asymptote? Let's go look at this graph. How many times does this function touch its vertical asymptote?
Twice?
Once.
Oh, wait. Yeah.
It touches it only at that closed dot. Those things are getting closer and closer to 2, but they're never touching it. What if I were to draw another dot right here? Is this still a function?
No.
No, because it doesn't pass the vertical line test. in order to be a function, no matter where you draw a vertical line, the graph can only touch one time. So a function, so that extra dot that I drew right there, it can't be there. It's no longer a function. So a function can touch its vertical asymptote only one time, otherwise it will no longer be a function. Okay, so we're gonna talk more about this later. I want us to add one more thing so that way we can really talk about expectations in all of the possible ways by the end of the day today. So that way next class we can really like go into depth and make sure you understand these.
Sorry.
Yeah, Ellie, what's up?
Yeah. So it can only touch it once. Can it touch it like multiple asymptotes? Or only
So
one?
it can touch every vertical asymptote once. So
Okay.
like, let's say that this one could have a point right there, this one could have a point right there, this one could have a point there, this one could have a point there, but
Alright.
each vertical asymptote can be touched only one time.
Okay, thank you.
Does that make sense? Okay, are there any questions before I add one last thing?
No, I think we're good to go.
Thank you, good. Okay, so sometimes we understand that a limit is an expectation. And to develop that expectation, I'm going and I'm looking at the left side and I'm looking at the right side and I'm being like, what does it seem like happening? Sometimes we're not going to be able to develop an expectation because sometimes things are going to be a little weird. So we're going to look at something now called one-sided limits. And this is something that we use when our expectation is different based on if I'm looking at the left side or if I'm looking at the right side. I'm going to draw a little graph, same as before, just let me know when you have the graph down. This is going to be a little bit of an easier graph to draw though. Let me know in the chat when you guys have the graph down.
Done.
Done.
Awesome. Okay, so it seems like a lot of you are done. So let's say that I wanted to consider what is the expectation at 1. So the limit as x approaches 1 of f of x. Actually, I'll call this f of x. So what is the expectation for the y value as x gets closer to 1? Well, no, typically we go to the left side and the right side and we make an expectation based on that. So let's go to the left side of 1. If I go to the left side of 1 and I go up to the graph and I follow their graph, so I like walk along the graph back towards 1, what's happening to my y value?
Getting closer to 2.
It's getting closer to 2, exactly. So on the left side of 1, it's getting closer to 2. What about if I were to go to the right side of 1? I go up to the graph and I follow that graph back towards 1. What seems to be happening to my y value?
Getting closer to 4.
You got it. So on the left side, I have this expectation of 2. And on the right side, I have this expectation of 4. Are 2 and 4 the same thing?
Oh.
No. So I can't really make I don't have a clear expectation as to what's happening. That said, I do have some ideas based on the left side and the right side. So we use what's called one-sided limits. And what I would do here for the left side is I write the limit as x approaches 1, but I give 1 a power of a little minus sign. And that little minus sign tells me approach from the left. And in this case, the answer is 2. When we looked at the left side, our expectation was 2. So that little minus sign right there, that's my expectation from the left side. If I want to do the right side, then I put a little power of a plus sign. And that plus sign tells me from the right side. So in this case, the answer is 4. So what we have here is what's called a left-sided limit and a right-sided limit. So my left-sided limit is the limit as x approaches, I'm gonna say a. We write a little minus sign.
It's so fucking boring.
What was that? Okay, so from the left side, my left-sided limit as x approaches a, that minus sign we read from the left of my function. And this is the limit as x approaches a from the left. And then we have a right-sided limit. And we read that the limit as x approaches a from the right of f of x. Okay. So what does this tell me about the limit itself? Here we said my left-sided limit was 2 and my right-sided limit was 4. So what's my expectation? If on the left we have 2 and on the right we have 4, do I have a clear expectation?
No.
I don't. So what that tells me is that that limit does not exist. So here we have existence of a limit. The limit as x approaches a of a function exists if and only if the left-handed limit is equal to the right-handed limit. So we're going to finish today just by using this to make a conclusion about the graph up there, about our original question up there. So what this means is we said the limit as x approaches 1 from the left was 2. Are these things equal to each other? Are these things equal?
No.
My left and right limits are not equal to each other, which tells me then that this limit right here does not exist because the left and right limits are not equal. So next time we'll do a lot more with one-sided limits, and we'll add another concept to this, but we'll still be working with graphs and we'll still be doing limits from graphs. So unless there are any questions, we are done for today.